Let us now prove this theorem that says, let's read it slowly. It says that for any collection of open sets, the union is always open. So the union of open sets is open. Okay. And then the intersection of closed sets is closed. This is in general. But now there is an extra. So these A and B are the key points of this theorem, the ones that work always. But then we have the two extras that are when we have a finite collection. Okay, we have a finite collection of open sets, then the intersection is also open. We just said that the intersection goes well with closed sets, but if the collection is finite, then open is also okay. And also when the collection is finite, the union of closed sets is closed. Okay, we just said that union goes well with open sets. Okay, so the things to remember here, the union goes well with open sets, intersection goes well with closed sets. And if the collection is finite, then no problem, everything works. So let's get to the proof. But before we do that, let me explain. You may be wondering why having a finite collection is important. Okay, let me tell you. Let's do an example first to show that if we don't require that the collections are finite, then C and D are impossible. They will not hold in general. So for example, let's say we have a Gn that is the open interval minus 1 over n, 1 over n. Okay, and this is, well, n equal 1, 2, and so on. So these are intervals from -1 to 1, -1/2 to 1/2, -1/3 to 1/3, and so on. Okay, so these are open intervals. So these are open sets. Okay, but when I take the intersection all the way to infinity of this Gn, I'm taking the intersection all the way to infinity because I want to show you why it is important that we require that the collection is finite in C, okay? So if I take the intersection all the way to infinity, I find out that the only point that is in all of these is 0. Okay, this is because 0 belongs to Gn for all n, and this is the only point that belongs to all of them for every n. Okay, any other point in the interval I pick will be left out at some point as n grows large. Okay, but what is the problem here? Because this is a single point, this is a closed set. Okay, so the intersection is closed. This violates C. Okay, so we are seeing here an example where we have the intersection of open sets being closed. But we can also do an example for D. Okay, so we can also say this is 1, and then 2. I could pick Fn that are, so let's say -1 plus 1 over n, 1 minus 1 over n. Okay, this is for every n. Okay, and in this case, we have our -1 to 1. Okay, let's say n bigger or equal than 2, maybe. So we will be growing from -1/2 to 1/2. Then the next one will be negative 2/3, 2/3, and so on. Okay, we are going to, in this case, we are going to grow our intervals. Okay, but you see what is happening here. What is the, if I think, because these are larger and larger, every set is containing the next. Okay, so the union of this Fn is always the last one to arrive. Okay, but if I take the, well, I can take from 1 to all the way, because if I take n equal 1, then I have only the point 0, but that's still okay. And then I can do the union all the way to infinity. Okay. And this union is going to be the interval -1, 1. Okay. Because basically because -1 and 1, they do not belong to any of these Fn. Okay, every single one of these sets Fn is leaving the points plus and -1 out, so they cannot belong to the union. Okay, but you see here the Fn were closed, but the union, the infinite union, is an open interval. Okay, so we see again that we need that the family is finite for that. So again, the moral of the story, as we saw here, the union of open is open, the intersection of closed is closed. So let's now prove this. Let me copy paste. Let's put that aside. Oops, maybe too much. So proof. For any collection G alpha of open sets, the union is open. So what do we need to prove here? So we need to show that a set is open. To show that the set is open, we need to show that for every point there is a neighborhood contained in the set. Okay, so let's say that we have a point X that belongs to the set we want to show is open. Okay, this is a union that can be finite or infinite, doesn't matter. But we have a point there. So that means that X belongs to G alpha for some alpha. Okay, and I know that this G alpha is open. So by definition, this means that there is a neighborhood okay, neighborhood of X such that n is contained in G alpha. Okay, but G alpha is contained in the union of all these G alpha by definition. Okay, and that's what we wanted to prove. In the end, this shows that for every, this means that the union is open. What we have shown here is that for every point in the union, we are able to find a neighborhood of that point completely contained in the union. Okay. Now, for the second part, here we want to show that the set is closed. Okay, so how do we show that the set is closed? Well, before we start, notice that we have proved that the complementary of the intersection here, it's always good when we are proving a theorem, see if we can recycle anything we already have, okay? And you see that there is a connection between part A and part B because the complementary of the intersection is the union of complementaries. Okay, so here we have a union just as before. And now notice, because F alpha is closed, we proved that its complementary is open. Okay, so we have a union of open. Therefore, this is open. Okay, and because the union of the complementaries is open, that means, look at the left-hand side, the complement of the intersection is open. So that means that the original set must be closed. And we are done here. Okay. So we have two already done. Notice here, I could have proved it by the definition. That would be completely fine. But once we have already proved theorems like we have, it's always good to see if we can reuse some of that knowledge, okay? Save time. All right. So what about C? So in C, is the same type of thing. We have a finite collection, G1 through Gn. Okay, in this case, these are open sets. And we want to work with the intersection. It's a finite number of sets, okay? We want to show that this is open. All right. Let me rearrange things here. There we go. I put a question mark so that it's clear that we are showing this. Okay, so let's pick a point. Okay, in the intersection. And now our goal by the definition is to show that there is a neighborhood around X, okay? But look at what happens here. Because X is in the intersection, that means that X belongs to every GI for every I, okay? The GI are all open. That means that there must be a neighborhood okay, for each of these GIs. Okay, let's do a picture here. So we have let's say 3 sets. This is G1, G2, G3. Here we have our X. Okay, and we could take several. Let's move like this. It's going to be better. I could pick, for example, a neighborhood like this. This is a perfectly valid neighborhood for G3 because it's contained. Okay. For G1, I could take. Yeah, let's bring this. It's like, there you go. I could take something like this. Okay, that would be N1. You see that it's inside G1, but it doesn't really respect G2. And I could pick them kind of randomly, but you could be, probably you are thinking by now that, hey, why don't you zoom in and just take a smaller one, okay? That is contained in all three, and you just stop, okay? And that's the idea, okay? The fact that you can take different neighborhoods. Okay, let me write this more properly. Each of these Ni containing the corresponding GI. Then you can take the minimum of the radii R1 through Rn, and then pick n as a neighborhood with radius r. This is a neighborhood of x with radius r. Okay, once you have done this, then n belongs to the GI for every I, and that means that n is contained in the intersection. Okay, because it's containing all of them. And this is what we wanted to show. So we wanted to show that given a point, we are able to find a neighborhood. Now, if you're thinking that this proof is super neat and it should work also in the infinite case, why doesn't it work? Well, you can pause the video if you wish, but the trick is here. Okay, notice that here you are taking the minimum of n quantities, and that minimum is still a positive number. But then the example we saw is precisely an example of this, where if you take infinitely many radii, then the minimum, the infimum in this case is 0. Okay, so you lose, there is no space to take a neighborhood. That was what happened in the example. The intersection was just 1 point. So there was no possibility of taking a neighborhood there. There was no space. Okay, and then the last one. Well, for the last one, we have our F1, Fn that are closed. Okay, and then we want to show that the union is closed. Okay. But then again, we do the recycling thing. So let's recycle part C. Just take the complement of this we were working with. Becomes the intersection of the complements of the FIC, which are open. Okay, these are open because the Fi are closed. So then we have the intersection of open sets, which is open. Because of C. Okay, here very important that the n is finite. And then if we have that the complement of a set is open, then the set must be closed. And that's it. This finishes the proof.